Now let's talk about the root test. The root test is kind of a specialty test, and it only works under very specific conditions. But it's like when it does work, it's a really easy test to apply generally and gets you a great, simple result. So you just kind of keep it in your pocket for those rare occasions where it does happen. Whenever your series has an exponent of n, that's where the root test really comes into play. Now, that might seem rare, but you can actually insert a power of n into a sequence using a little bit of algebra. So for instance, if you just have a term n, and you want to make that have a power of n, you can rewrite this as n to the 1 over n raised to the nth power. Because 1 over n raised to the nth power, those multiply and cancel out back to 1. And then, one thing that's nice to know is this limit right here. It's the limit as n goes to infinity of n to the 1 over n equals 1. And you can prove that pretty easily just by using a table. So the root test, it actually looks very much like the ratio test. We have to compute a limit. So the value of this limit right here, so it's the limit of the nth root of the absolute value of your terms. So again, this is tells us if it converges absolutely. If that limit is between 0 and 1, then the series converges absolutely. If it's greater than 1 or infinite, the series diverges. And then if that limit is equal to 1, the test fails, does not provide any information. So very similar to the ratio test in that respect. Let's jump into some examples here. And here's a pretty standard example for root test. So I have the series as n equals 1 to infinity of some function raised to the nth power. So just everything's raised to the nth power. And when you see that power of n, that's a clear indicator that you should probably use a root test here. So all we would need to do is calculate a limit as n goes to infinity of the nth root of all this. And to be honest, you really can skip this step of writing the nth root because it's always just going to cancel out the power of n anyway. That's the whole point of the nth root. And I suppose I should have used absolute value in there. There. So we're going to end up with effectively the limit of the absolute value of 5n to the 4th plus 1 all over 7n minus 2n to the 4th. The result here is a rational, and we're taking an infinite limit of a rational function. The degrees here are equal, so that means the limit's going to go toward the ratio of the leading term coefficients, which would be negative 5/2, but we do also have these absolute value bars, so it's actually going to positive 5/2. And that is bigger than 1, so we've proven that this series diverges by the root test. So, as I said, when it applies, it's generally pretty straightforward. So let's look at some other examples. Here's another. So we have the series from n equals 1 to infinity of e to the 2n over n to the nth power. Now, this particular series, it might not be entirely clear exactly how the root test applies to start with, but if we do a little bit of algebra, we can reveal a power of n, I think, pretty easily. Because e to the 2n, using rules of exponents, we can write that as e squared to the nth power. Now you can probably see where we're going with this, because there's an nth power on both the numerator and denominator, which means I can write that as a single fraction raised to the nth power. And now the root test is going to very easily apply. So this is going to be the limit as n goes to infinity of the nth root of this series. Well, I guess a sequence at this point. That's all right. And that's going to be the limit of e squared, whoops, it doesn't look much like a square, over n. E squared, even though e is generally considered a function, it's only a function if the exponent is a variable. E squared is a constant value. So we have a constant over n. So the denominator is changing, it's going to infinity. This limit is going to go to 0, and therefore this series converges by the root test. Okay, here is another. This one looks like it's going to be fairly similar. We can certainly do a little bit of rewriting at the start in order to show how the root test really applies. But I could write this as n over the natural log of n, all to the nth power. So then my root test would be the limit as n goes to infinity of the nth root of all this. And like I said, you don't necessarily have to write the nth root down each time. I'm only really doing it for emphasis here, because it's always going to just cancel out that exponent. So then that's the limit as n goes to infinity of n over the natural log of n. Now, this particular limit might not be quite so clear as to exactly what's happening. But remember, you can always evaluate a limit in different ways. Generally speaking, I try and use L'Hopital's rule whenever possible. It's usually a fairly clean result and easy thing to do. But you have to have a limit that's infinity over infinity, or can be written in that way. So that is the case here. This is an infinity over infinity type. So I can take the derivative of the numerator and denominator. The derivative of n is 1. The derivative of the natural log of n is 1 over n. So this ultimately is the limit as n goes to infinity of the absolute value of n, which is going to go to infinity. And since that's infinite, that gives me a result. It's only at 1 that the test fails. So this gives me a result and tells me that this series diverges. And L'Hopital's rule is actually fairly similar to a lot of what we're doing here anyway. It's a good thing to bring up. We're effectively seeing, by taking the derivatives of each of these functions, we're seeing how quickly they're changing. That's what the derivatives tell us. So if the numerator is changing faster than the denominator, then we'll end up getting a limit in the next stage as n goes to infinity. So we're looking at how quickly things change and go to infinity. That's the basis of L'Hopital's rule. All right, here's another one. Now this one isn't entirely clear how the root test might apply right from the beginning. However, I'm going to use it because there is this nth power in the denominator. And let me show you how it can apply even if there's no nth power in both the numerator and denominator. So limit as n goes to infinity, the nth root of n over 5 to the n, oh, and there's no nth power, force of habit there. Okay, so when I take this nth root of a fraction, can actually do the nth root of the numerator and denominator separately. So I could rewrite this as the nth root of n divided by 5, because the nth root of 5 to the n, well, that cancels that exponent. And then, just to make this a little bit more clear as to something we had earlier, the nth root of n is the same thing as n to the 1 over n. And we said that that limit, as n goes to infinity, is equal to 1. So that was a result that I mentioned at the beginning of the root test. And so you can just use that freely. You don't have to go through a table to prove that. So what that means is this limit's going to 1/5. And if that's going to 1/5, that is less than 1. So this series converges by the root test. So having an exponent of n generally is a good indicator that the root test might apply. There might be another test that's a better choice, but you can always give it a shot.